Hi everyone, this is video 18, and today we're going to be talking about quantifying efficiency and efficient programming. So today's video is going to have a little bit of a different flavor than the past videos in that it's going to be a lot more theoretical, in that I'm going to go into a little of the mechanics of how we quantify efficiency of computer programs. And for those of you who love math, you're going to really like this video because you're going to see how some math that you've learned in high school is applicable to the field of computer science. And even if you don't like math, maybe you'll find this interesting because you can finally see how the math you've spent so long in school learning, it can be simple math even, can be used to understand efficiency of computer programs. A very, very important topic. So, with all ado, let's begin. This is actually one of my favorite topics, so I'm really excited for this video. And to start off, I'm just going to grill you from the beginning. We're going to start with a math question out of nowhere. So let's say we have the following function, a function of n that's equal to 10n squared plus 124n plus 10,000. So my question to you is very purposefully vague in that I want you to think about as n becomes very, very large. So we're talking really large n. Which of the following functions does n quote-unquote look like? So again, very broad question. Take some time to think about what you might think the answer is. And I'm going to spoil in 3, 2, 1. The answer is n squared. And so why is it n squared? Well, there are three approaches to solving this problem. The first way is that more of an informal but valid way. The second way is a formal way using limits and a little bit of the limits and the calculus that goes along with limits. And then, of course, there is the easy way, which I'm going to talk about. So let's start with method 1. So method 1 is the informal but very valid way, and actually I think it's pretty smart. So the question asks you, hey, as n becomes very large, what does this function look like? So the first thing that might pop up into mind, what happens if I put a larger number in it? So I'm going to plug in 100,000 into my functions f of n, and also my choice, my functions that I have a choice of choosing from, basically, because then I can tell whichever one's going to be the closest is going to be my answer. So if I plug in 10,000 into this function, I get this large number, and if I plug in 100,000 into these functions, I get the 10 to the power 20, 10 to the power 15, 10 to the power 10, 10 to the power 5, and 10 to the power 4. So, which one is this number closest to? Well, with some analysis, you can find that this number ends up being closest to n squared, which is our answer. So, this is one very viable method of solving this problem, even though it's not very formal. It's a little bit of guess and check kind of method, but it still works. Alright. Now, next I'm going to talk about the formal way to approach this problem using limits and the calculus that goes along with that. But if you haven't talked about limits, go ahead and you don't have to. You can ignore this entire part of the video. I'm going to spend like a very brief amount of time on it and it doesn't really matter honestly because the third way, in my opinion, is so much better. But for those of you who are interested, I want to show you that there is a formal way to approach this problem. So, the way we can construct this problem is as n gets very large, we can think of that as n approaches infinity. And we want to basically find a function g of n that's as close to f of n as possible when n becomes very large. So what does it mean to be close to? Well, we can define that as being within some non-zero constant of f of n. Why do we want to define it as constant? Because generally, when limits approach infinity, it's either the k value is either going to be 0 or infinity. Because it's either f of n is either going to be much greater than g of n, or f of n is going to be much less than g of n. And in both those cases, we get infinity and 0 respectively. So what we want to find is a case where we don't get infinity or 0. And that case is where we get a non-zero constant. So if you remember studying horizontal asymptotes, I believe is what it's called. Or actually, no, sorry. Is it horizontal? Yeah, it's horizontal asymptotes. This is how we can calculate this limit. Okay. So let's look at this. So if we approach infinity and we basically plug in f of n and g of n, we can see that we get the following limits. So in this case, we get a limit of 0 because n to the power of 4 is much greater than 10n squared plus 124n plus 10,000, and same in this case. And now, the only case where we get a constant, a non-zero constant, is this case. And why is that? Because as n approaches infinity, this is roughly going to equal 10n squared over n squared. Because what's going to end up happening is these lower order terms, they're not going to matter. Because n is so large that 10n squared dominates the entire function. So we can say that this approaches 10. And that's why this is the answer. So that's the formal way to do it. Now, I'm going to talk about the informal way. I mean, sorry, not the informal way, but the easy way. So what we're going to do is we're going to kind of take the ideas of a limit concept and just adjust them in a way that makes it easy to understand. So what we're going to do is the first thing we're going to do in method 3 is we're going to look at only the largest term. So what's the largest term in this? 10n squared. By largest term, I mean highest order term. So 10n squared is going to be much greater than 124n and 10,000 when we're looking at large n. Okay, we're also going to ignore all constants. So when we have 10n squared, we're just going to treat it as n squared, because at the end of the day, if you plug in a billion to this function, there's not really going to be a difference between 10 tens of billion squared versus just a billion squared. So that's why we ignore constants. And so when we do this, we first get 10n squared, and then when we eliminate the constant, we get n squared. And hey, that was our answer. So this is actually a very important concept and a very important simplification that will come back when we talk about efficiency and something called big theta notation. So I will point out when this idea comes back, but there is a reason to this mad math problem that I'm giving you that seems to have nothing to do with anything. But I promise you, there's a reason. Okay. Now, let's analyze a little bit of this function. So we want to basically find, our motivating question is, how can we calculate the efficiency of such a function? So the way we're going to do that is, let's just think of some methods off the top of our head. One method we could do is we could time the program. So for various inputs, we could just set up a timer and see how fast the program runs. So this is a very literal definition of efficiency. And it's good because it's easy to interpret the meaning, because obviously if one program takes 100 seconds to run versus another program taking 1 second to run, the 1 second program is much more efficient. So it's easy to interpret. But the bad thing is that this could vary from computer to computer. So for example, if I ran a program on my laptop right now versus a supercomputer running the same exact program, the supercomputer is going to be much faster. Does that mean that program is more efficient than this? Not necessarily, because it's the same program. It's just because my computer is inherently a little slower than a supercomputer. I mean, not just a little slower, a lot slower. But because of that, we get a different idea of efficiency. So this measure of efficiency is not really standard across all computers. And we want to find a standard definition. So we can do better. So a better option is potentially, hey, can we count the operations of some type of operation on a fixed input size? So what does that mean? Well, basically, think about this function. What are the two things I can think of, two operations I can immediately see, is that we're iterating through a range. So that means we're binding I. So every time we iterate through the for loop, we're assigning I to a value. So how many times does that happen? And then the next operation we're going to look at is the execution of inside the for loop. So evaluating this Boolean expression context, I double equals element. So how many times does that execute? So these end up actually having the same count because they're basically counting the same thing. So in the best case, we only have one iteration of range, because what's going to happen is if this ends up being evaluated true, we're just going to return I, and then we're going to be done. So we're going to have at least one iteration for sure, but so that could be the best case. But if this ends up being false every time we go through the for loop, how many times are we going to bind something to I? Well, if we have n is equal to 10,000, we're going to iterate through this 10,000 times and assign I 10,000 times. So we're basically counting the operations. So based on an input, we see how large an operation is, or how many operations something happens. So this is good because machine independent. Even a supercomputer is going to have to do the same type of number of operations. But the problem is that it's based on the input. So if I give it 10,000, I get 10,000, but that doesn't really tell me much, you know? So there's a better option. This is getting there, but the best option is actually option 3. And option 3 is that we're going to determine a measure of the runtime as a function of the input size. So we're going to go off that same idea of analyzing an input size, and what we're going to actually do is we're going to define an operation like the last time, and what we're going to call this operation is a cost model. And what we're going to do is we're going to count this as a function of n. So if on the previous slide you saw that the count when n is equal to 10,000 is at least 1 or at most 10,000, and same with the execution of I double equals element. But if we do this as a function of n, so for any n, the worst case is that it executes n times. Or the best case is that it executes once, and the best case being that if this ends up being true. So whenever we look at efficiency of a program, it's good to think in terms of best case and worst case. Now, as computer programmers, we like to be a little pessimistic when it comes to efficiency. We always want to prepare for the worst case. So the runtime of a function is generally going to be in terms of the worst case scenario.